Hey guys, welcome back to the QSC YouTube channel. Today we'll be recording the chapter 7 from 7.1 to 7.4 quiz for physics. Okay, which of the following are the results obtained in Rutherford's experiment? Okay, Rutherford's experiment was like he was trying to, how can I say it, prove or debunk Thomson's theory. Thomson's theory is like the pudding theory where there are electrons in a positively charged medium, which is obviously false. So Rutherford made a theory where this is the nucleus with protons and neutrons, and then around it there are electrons, tiny dots orbiting around it. Okay. Which of the following are the results obtained in Rutherford's experiment? Most of the atom is empty space. The nucleus of an atom is positively charged. This is because the nucleus has only protons and neutrons, which obviously the net charge is gonna be positive. Most of the mass of the atom is concentrated in a small heavy nucleus. This is because electrons are very small with nearly negligible masses compared to the nucleus where it has a really large mass. Question 2. Okay, they're asking which of the following nuclides are of the same element. So nuclides of the same element will have the same atomic number, and but they could have a different mass number. As long as they have the same atomic number, they're the same element. Number 3. For question 3, which of these samples can be used as a radioactive source in Rutherford's experiment? Okay, so look, I didn't do much research into this, but from what I read of the book, okay, Rutherford's experiment used alpha decay, so which is why we used radium and radon. Okay. Which of the following nuclides have the same amount of neutrons? So we know that atoms are like A, which is, wait, no, it's not A, it's Z, then A. Z is the atomic mass or the number of protons. A is the amount of number of nucleons. Nucleons are protons plus neutrons. So how do we get neutrons? All we need to do is A minus Z. Okay, so now let's start with neon. Neon has 23 nucleons minus 10 protons, which is equal to 13 neutrons. Here, carbon in this case has 12 nucleons minus 6 protons is equal to 6 neutrons. Here in aluminum, 25 nucleons minus 13 protons is equal to 12 neutrons. Here in magnesium, 24 nucleons minus 12 protons is equal to 12 neutrons. And then again for sodium, 23 nucleons minus 11 protons will give us 12 neutrons. So all of these three have the same amount of neutrons. Number 5. Which of these will be enough to protect against a flux of beta particles? Okay, now for this question, we need to know the strengths of the different types of particles. Alpha is the weakest, and it is like it can only go through like think 1 centimeter of air. Meanwhile beta can go through 5 centimeters of air, or one sheet of paper, one paper. While gamma is the strongest, gamma, one of the only things that can stop it is lead. And lead is so far the only thing that we took that can stop gamma. So here, which of the following will be enough to protect a flux of beta particles? So it's everything except the ones that I mentioned here. Okay. Question 6. Which of the following will be enough to protect against a flux of alpha particles? As I said in the last question, alpha particles are the weakest of the types of radiation. So, as I said before, alpha can be protected against everything except 1 centimeter of air. Which of the following correctly describes the properties of photons emitted during radioactive decay? So photons are basically gamma particles. Okay. As we know, light, or photons in this case, they move they move in a straight line. They're not line, but like their movement is like light and they have the speed of light. Gamma is not positively charged. It is neutral. And as I said, it's not 6% of the speed of light. It is referred to as gamma radiation, and their ionizing ability is the weakest out of all the radiations, which is why and the ionizing ability of gamma should be memorized, and it is 10 ion pairs per 10 centimeters of air. And as I said, photons pass in straight lines through uniform matter. Number 8. Complete the following diagram to describe Chadwick's experiment setup. Okay, so what Chadwick did, he proved that there are tiny particles the same size as protons that basically that are also located in the nucleus called neutrons. He did it by lining up beryllium, paraffin or wax and a detector next to each other, and of course the radioactive source. So the source emitted alpha particles, which is a helium isotope, and then once it went through the beryllium, neutrons came out, and then once it went through the wax, protons came out. This experiment is something to be memorized. This particular nuclear species having specific values of Z, an atom of iron Fe is neutral. This particular species having specific values of Z and N is called a nuclide. Z and N is basically the atomic mass and the mass number, which we know from chemistry, and it's called a nuclide. A neutral Fe has 26 protons, which is the number at the bottom right here. 30 neutrons, which is, as we said before, is the mass number minus the atomic mass equal to electron. Here, not electron, sorry, is equal to neutron. Okay, and then electrons is normally, if it's a neutral atom, it is the same as the atomic number. Number 10. An alpha particle is released by a nucleus of an unstable atom. Okay, so look, let's say we have carbon 614. which will give us, okay, so look, this is the alpha particle. Since it's helium, we need to memorize that it has an atomic number of 2 and the mass number of 4. Okay, plus. Then here let's call it element X. So here we need to like basically balance it out. So here we do minus, then here we do minus. So the atomic number will be 10 and the mass number will be 10 and the atomic number will be 4. And as we can see, like here, like the mass number decreases by 4, but the atomic number decreases by 2. Okay. Question 11. Consider the nuclear reaction shown below. Choose the correct answers. Okay. The reaction shown is an example of a beta plus decay. So, yeah, this is something to be memorized as well. And the particle labeled Y is a positron. A positron is basically like, it's a beta particle, but normally beta particles are, excuse me for the bad handwriting, so this would be beta minus, and this is beta plus. So we would recognize that it's a beta plus and a positron because it's positively charged. And then the value of X would be, here let's me zoom in. We would just do 12 minus 0, which will give us 12. That's it. Okay, let's move on to question 12. Radioactive materials should always be securely stored when not used. This is because they are really dangerous. Even if you're looking at it or using it with your hand, it's really dangerous. Material that is best used for lining the box in which radioactive materials are stored is lead. Because as I said before, lead is basically overpowered, you can say, to all types of radiation. Except for gamma, it only reduces the speed. Reduces the initial value. So, yeah. 10 centimeter walls of lead will completely stop alpha and beta radiation and reduce gamma radiation to 10% of its initial value. Okay, a charged particle is released as a result of radioactive decay. So look, let me, like, how can I say this? Rank the radioactive particles in terms of speed. Gamma is the fastest, basically moving at the speed of light. Beta moves at a speed really close to 0.98 times the speed of light, or 98% of it. And then alpha is the slowest, moving at 0.06 times the speed of light. This is in terms of speed. But in ionizing ability, let me just put ion, then alpha is the greatest, producing 10 to the power of 5 ion pairs per centimeter traveled in air. Then beta produces 1,000 ion pairs per centimeter traveled in the air, while gamma only produces 10 pairs of ions in the air per centimeter, gamma. So always beta is in the middle, no matter what. Number 14. A radioactive source R emits radiation into the space where electric field is maintained by two oppositely charged plates, as shown in the diagram below. Okay, look, we know that alpha is positively charged, right? Okay, positive. which is why it will go attract to the negatively charged, which is why here it's alpha. And as we can see here, the detector A is closer to the negatively charged, which is why it has higher activity. What material of the shield will ensure a narrow beam of radiation regardless of its nature? We already spoke about this, and it's lead. It's basically the kryptonite of radiation. Consider the tracks in a cloud chamber exposed to a certain radiation. The tracks in the cloud chamber are left by a condensed liquid. The radiation that leads to the creation of such tracks is most likely gamma radiation. Look, so if you see this pattern, you're gonna have to memorize that it's gamma radiation. Which of the following is true about the presence and the direction of the magnetic field? It is impossible to tell since this type of radiation is not affected. So look, all radiations, alpha and beta, are affected by magnetic field except for gamma, it's not affected. Number 16. A radium source emits three types of radiations in a magnetic field. The tracks formed in the cloud chamber by these radiations are shown below. Okay, so look, we're gonna have to memorize that if it's into the plane of the picture, this will be gamma. Alpha will be like this, while beta will be curved like this, which is what is right here. Number 17. A GM tube detects background radiation of 750 counts in 5 minutes. Okay, look, so to know background radiation, BGR, it is equal to counts over seconds. Count over S. S in this case is seconds. So we do 750 over 5 times 60 to convert it into minutes. 5 times 60 to turn it into minutes, which 750 over 300, which is 2.5 BQ. The major source of background radiation is radon decay. This is something which we have to memorize, and it's in the book. Number 18. The area of the GM tube circular window is 2 centimeters squared. In the absence of the radioactive sample, the tube's readings are 200 BQ. When the sample is placed 60 centimeters away from the tube, the readings of the GM cube are 170 BQ. Okay, look. So to find the detected radiation rate only due to the source, we do the readings minus the background, the tube's readings without the radioactive sample. So basically I'm gonna call it A, or absences. So 170 minus 20 is 50, which I'll call DR. Okay. The total radiation emitted by the source to 2 decimal places is. Okay, look, so for part B, there is a rule to find the total radiation emitted, which is 4 times pi times r squared times the dr over the area. Okay, so let's do this. 4 times pi times Look, since here it's in centimeters, we're gonna have to turn 6 centimeters to meters times 0.06 squared times 150 over, look, so we need to convert 2 centimeters squared to meters squared. To do that, we need to divide by 10,000. So 0.0002, which is equal to 33929. 33929. Since they're asking here to times 10 to the 4 or scientific notation, so you take 4 back. 1, 2, 3, 4. So we get 3.39 to 2 decimal places. Okay, now we move to question 19. Consider a neutral atom of iron. Okay, the atomic number is always the one down, 26, and the mass number is the one up, 54. Mass number, as I said before, is the number of nucleons or protons plus neutrons, while the atomic number is the number of protons. Number 20. Look, as I said before, this is basically a question asking about each strength of the types of radioactive particles. So as we said before, alpha is the weakest, which goes through only one paper. Beta particles go through a book or like 5 sheets of paper. Gamma rays go through a book. They do not go through that, or they barely do. Okay. A radioactive source emits radiation into the space where a magnetic field is present. The source emits alpha particles and gamma radiation. 3 detectors A, B, and C are used to detect radiation. Okay, look. So as we said before, gamma particles are straight, but in this case, alpha particles go like this, since this is into the outside of the plane of the image. So if we see circles, this means that it's outside the plane of the image, so it's gonna go like this, and which is why detector C will detect alpha particles. A radioactive source emits radiation into space where a downward electric field is present. The source emits beta particles and gamma radiation. 3 detectors A, B, and C are used to detect the radiation. Okay, again, as we said in the last question, gamma goes straight, which means detector B will detect it. Since we know beta is negatively charged, okay, it will move to the positively charged place, which is where A is, which is why A will detect beta particles. And detector C will have 0 radiation detected because, of course, gamma particles, as I said, will go straight, and beta particles, because they're negatively charged, they will not go to the electrons. They'll be repelled going up, or in the opposite direction. Number 23. Okay. Now this is basically describing the different types of decay. Alpha decay alpha is a helium nucleus. We already discussed this. With a mass number of 4 and an atomic number of 2. And beta is an electron, as I said before. Beta is negatively charged. And gamma decay is a photon, as I said again. And then the least ionizing effect is gamma with 10 pairs of ions per centimeter of air. Number 24. An unstable nuclide emits radiation in an attempt to become more stable. This is known as radioactive decay. This is also something to be memorized. Number 25. Fission occurs when two light nuclei fuse together to become one heavy. So it's basically like this plus this is equal to this, for example. Number 26. Drag and drop the picture to describe the tracks left by different particles in the cloud chamber. Alpha particles leave thin, or wait, yeah, thick straight lines. Beta particles leave wisps like dotted lines, like this. While gamma particles leave thin but like really clear straight tracks. Thank you guys so much for watching this video. I hope this video benefited you, and if this video helped you studying, please like, subscribe, and hit the notification bell. Thank you again so much for watching this video, and goodbye.